Now that we've established how to find a line, and in general how to tell if a particular point is on a line or how they intersect, we'll actually look to see something that's even easier to determine these situations. Let's suppose we have two lines. In general, there are three things that could happen. The first is that, what if the lines are the same? We've already discussed how we can have multiple forms of the same line, so it may not be immediately obvious. If these lines are the same, then that means u minus w and v are both multiples of z. We consider in this case the v and the z to be like the slope, and here we just need them to be multiples. And then u minus w, these are like our intercepts. And in this case, since they're not exactly intercepts, we actually need to subtract to see if they are the same as the slope, or at least a multiple of it. The second case, what if they're not equal, but they are parallel? In this case, these are distinct and parallel if v is a multiple of z, but u minus w isn't. For them to be the same, we needed both v and u minus w to be multiples of z. Here I only need v, and u minus w can't be. This is guaranteeing that we have different intercepts on the y-axis. The next case that we'll consider is if they intersect at a single point. These lines intersect if u minus w is in the span of v and z. And you can see this at the last example in the parametric vector form video, where we looked at to seeing if two lines were intersected. We set them equal, and what we ended up doing is checking whether or not u minus w was in this span. And it's important to note that these three situations are not the only three situations that can happen. While they are in our two-dimensional plane, these lines can be in any dimension. And if we consider something in 3 dimensions, we can have lines that don't intersect but are not parallel. Now that we've discussed lines, we'll look at planes. And with planes, there's actually 2 different ways to represent them. The first is parametric vector form, which models our formula for lines. We have u plus tv plus sw. Finally, our normal form looks like this. a1x1 plus a2x2 plus a3x3 equal to 1. However, it is important to note that this guarantees that our plane does not pass through the origin. If it does pass through the origin, then instead we set it equal to 0. And that's the only case where we can't have it equal to 1. Let's consider this plane, which isn't quite in normal form, but it's pretty close. All we would need to do is divide through by 8. However, we actually want to move this to parametric form. And we do this by solving for x1. We get 8 over 7 plus 4 over 7x2 minus 5 over 7x3. Therefore, when I think about moving this to parametric form, I have this formula for x1, 8 over 7 plus 4 over 7x2 minus 5 over 7x3. I don't have anything for x2 or x3. Now when I try to break it up, I have my constant vector plus x2 times anything that involves an x2, in this case 4 over 7, 1, and 0. I'm running out of room here, but we would then need to add our x3 vector. In this case, negative 5 over 7, 0, and 1. And now this is in parametric vector form, and we can see that we do have 2 variables rather than 1 like we did with a line. Finally, let's consider the plane passing through these 3 points, and I want to write this in normal form. Well, to do that, we're going to have to think about what normal form is. a1x1 plus a2x2 plus a3x3 equal to 1. And since these vectors are all on this plane, they should all satisfy this equation. So I should have 2a1 plus 0a2 plus a3 equal to 1. V gives me negative a1 minus 2a2 minus 3a3 equal to 1. And then W, negative 7a1 plus a2 minus 3a3 equal to 1. I can see that this is just a system of equations. So we'll start by putting this in a matrix. And then we just need to row reduce. And we'll skip the steps here and just give the row reduction. And when we do, we get 1, 0, 0, 0, 1, 0, 0, 0, 1, and then on the right, 4, 8, minus 7. Therefore, my normal form is 4x1 plus 8x2 minus 7x3 is equal to 1.